In this video, we're going to talk about compound interest. Compound interest is when the interest is accumulating either as an investment where you're earning the interest or in a loan where you're paying back the interest. We're going to look at two ways that this interest can accumulate over time. The first type of interest is called periodic compound interest. And for this type, the interest is added into the account after a set period of time. Maybe it's a certain number of times per year that the interest is added. This is usually called the compounding. It talks about how often the interest is added. So there are two formulas that we'll look at in this video. But before I lay out the formula for you, I want to give you a general idea of how this works. So I like to take a simple example like this one and show you what's happening year by year as the money is growing. This table that I'm going to use is just a demonstration. It's not anything that you will be required to replicate. It's just to kind of show you the logic behind the formula that we're going to use so you can understand it a little bit better. Okay, so let's suppose that we're going to deposit $1,000 in an account at 6% interest, compounded annually for 3 years. This compounded annually here means that the interest is going to be added one time per year. Okay, and the 6% interest that's mentioned here is the annual interest rate. So every year I'm going to earn 6% on the amount that I have in my account. So we're assuming that we're depositing that $1,000 at the beginning of this time period, and we aren't depositing any additional money. We're just looking at what happens to that $1,000. So at the beginning of this experiment, 0 years have passed. We have our $1,000. Then, after 1 year has passed, we're going to earn our 6% interest. So just to calculate that sort of in the normal way, right? I have my $1,000. And then I'm going to take my 6% and convert it to a decimal and multiply that by 1,000 to get the amount of money in my account. This would be my principal, the money I have in my account, plus interest to give me the accumulated value or the future value. Okay, so we could multiply this out, right? I have my calculator here, so I'll just do that off to the side. Probably we could have done this one in our head, but we get $60 in interest. Just to give you an idea of the pattern, if I were to take this, what I've written here, and factor out a 1,000, I'll have 1,000 times 1.06. Right, and when I multiply by the 1, that's giving me the principal. And when I multiply by the 0.06, that's adding the additional interest to that principal. Okay, so that's first year. Now in year 2, this is where compound interest gets interesting because I'm not earning my interest on the $1,000 anymore. At the beginning of year 2, I'm starting out with $1,060. So I'm earning my interest on my $1,060. And so again, we could put that into our so altogether, if I add that up, I have $1,123.60. Okay, and in this section, this may be a good time to mention, we're dealing with money, so it just makes sense to round to the penny, right? So we're going to do that. Okay, as far as the pattern goes, I could factor out the 1060 and I would see another 1.06 here. But remember from the line above, 1060 was 1000 times 1.06. So if I put those two factorings together, really what's happened since the beginning is I've multiplied twice by 1.06. Okay, we're talking about 3 years here, so this is the last year. And maybe you can see the pattern that's going on here. So I'll just fill in just like we've done previously. So now I'm earning 6% on the 1123.60. And so I end up with $1,191.02. Okay, and the same thing's true here. I could factor out that 1123.60 to get one more 1.06 that's being multiplied. So for compound interest, we are not just earning interest on the original amount, we are earning interest on this new accumulated value. So each year we're earning interest on our previously earned interest. And that sounds really great. Okay. All right. So maybe you can see this. We're going to use an A in a minute to represent the future value. But to calculate this, what happens to this $1,000, that 1 plus the percent change is coming into play here. That's where we get the 1.06. And we did that for 3 years. And that came out to be this $1,191.02. Okay, I have one more example like this to show you because I want to give you an idea of what happens maybe when I calculate the interest more often than once a year. I want you to see how that changes things before we look at the general formula. Okay, and I'm going to keep a lot of things the same so you can kind of see a comparison. So I have the same amount. Let's say I'm going to deposit $1,000 in an account at 6% interest again, this time compounded semi-annually for 3 years. Semi-annually, that means 2 times per year. So every 6 months, I'm going to be earning interest. Okay. So let's do the same experiment. No time has passed. Starting out with my $1,000. Okay, now because I'm going to add the interest in twice a year, half a year has passed, 6 months. Okay, now this, like we said earlier, this 6% interest is the annual interest rate. Which means I earn 6% every year. So I don't get, even though I'm calculating my interest 2 times per year, I don't get to have 6% and then another 6%. That would be like really awesome in terms of earning interest, but it doesn't work that way. So we divide up the annual interest into equal parts, right? So since I'm doing it 2 times per year, 6% divided by 2, I earned 3% each time now. So I have my $1,000, 3% as a decimal. It looks something like that. If we calculated that out. Okay, okay, we get $1,030. Maybe we should say, okay, this adds 3% interest 2 times per year. Okay, and I can do that same sort of factoring if I factored out the 1,000. I have the 1, like we said earlier, represents the principal or the money I currently have. And then the 0.03 that I see here is going to also add in the interest and give me the total accumulated amount, principal plus interest together. Okay, just like before, as I'm entering the second half of the year, I do not earn my interest on the 1,000, I earn my interest on the 1,030. So this is really great because even just in the span of 1 year, I'm earning more than just 6% because I'm earning interest on the previous interest I just earned. Okay, so we could plug that into our calculator if we wanted to. So if I add all that up, this comes to $1,060.90. If you compare that with what we had after 1 year doing the annual interest, we had $1,060 when I earned the interest 1 time a year. Now I have $1,060.90. Woohoo! So I did earn a tiny bit more. Now keep in mind, that's just over the course of 1 year. If I'm making a long-term investment for 30 years, that can be some pretty big growth, right? Pretty substantial interest that I'm earning there. Okay, now we could continue this pattern. So if I factored this out, right, I'd have another 1.03, and remember, just like before, the 1,030, I could do that factoring. So altogether, this is like having multiplied by 1.03 2 times now. Okay, and we could continue. I don't know if it's worth it to go all the way here. Maybe we should just do a ... Can you get a good feel for the pattern here? This time I'm earning 3% interest 2 times a year, and every 6 months I'm earning interest on the interest I've already earned. So it's accumulating faster than it would if I were just calculating it 1 time. Okay, so let's jot down here what's going to happen. So I started with my $1,000. This is the 1 plus the percent change, and this time I'm earning 3%. So at the very top, we said we're looking to determine how much money do I have at the end of 3 years. Since I'm doing it twice a year for 3 years, that's 6 times that I'm going to add the interest. So if I put that into my calculator, and you could definitely continue that chart, but I didn't want to dwell on it too much in case you were ready to move on. So if I calculate what that is, I will have earned $1,194.05. We compared that with what we did on the previous page when we were doing annual interest. Okay, it is a little bit higher. We earned about $3 more over the course of those 3 years. Again, this is a very small amount of time. $1,000 is a very small amount of money. So if you are investing in your retirement, okay, and they say you need to start now, start early so that you can have a long period of time, 30 years, to be investing, and this you can make good use of this compound interest idea, right? This building up of interest, because it can build up very rapidly. Okay, so now that we've gotten a bit of an idea of what this calculation looks like, now maybe we're ready to look at the formula. So here's the formula for periodic compound interest. So we've already been using A as the future amount. I think the variable A stands for the accumulated amount, so you could call it that also. P is the principal or the starting amount. The little r is the annual interest rate written as a decimal. N is what's called the compounding. This is a number of times per year that the interest is being added. And T is the time in years. So the N, let's speak about that because this sort of makes this formula unique. The N is going to appear in the problem as some kind of a keyword. So far we've done annually, that would be N equals 1. Semi-annually, that would be N 2 times a year. Quarterly would be 4 times per year. Monthly would be 12 times per year. Okay, you get the idea. All right, so let's try the formula out with this example here. So it says if $950 is invested at 3%, compounded daily for 20 years, find the future value of the investment. So compounded daily means N is, there are how many days a year? 365. Okay, and we can plug all of this information into our formula. We're looking to find the future value, so we don't know A. The principal is our $950. We have 1 plus, our interest rate is 3%, so 0.03. Divided up into 365 parts. That is a lot of parts, okay? Raised to the n times t power. So 365 times 20. If I'm going to do it every day for 20 years, I need to multiply by that growth factor every day. That's a lot of days. Okay. So I want to calculate this. Now your calculators can do this all in one shot if you add enough parentheses. So if you wanted to put it all together in one shot, you might want to add an extra set of parentheses right there. Because I am in the habit of using a scientific calculator, I usually start by doing from the inside the 0.03 divided by 365. I leave that in my calculator, add 1, and then I'm going to raise it to the 365 times 20 power, and then multiply it by 950. It's definitely not the only way to go about this, but that is one way you can do this calculation without having to round somewhere in the middle. It's always a good idea to round, to try not to round until the very end. And notice for all of these, we're going to round to the penny. Okay, so this is called periodic compound interest. The second type of compound interest we're going to look at is continuous compound interest. Continuously compounded interest. All right. We've been using A. I don't know where that S came from. Okay, so we have A equals P times E raised to the RT power. I usually think of this one as PERT, that shampoo, PERT. Okay, so the E here is that Euler's number, the 2.71828, etc. number. Okay, so it's not a variable. I didn't type this out on this page, but everything else has the same meaning. So A is still the future value or the accumulated amount. P is still the principal. Little r is still the annual interest rate as a decimal. And T is still the time in years. So I'm not going to derive this formula because I think that would be maybe a little bit of overcomplicated for our class, but there is often an explanation in the book, although I didn't find it in your book this time, so I copied it here, about where the E comes from, right? Because it does arise out of the periodic compound interest formula. So the continuously compounded interest, the idea is that we are constantly adding interests, more than every minute, more than every second, right? The interest is just a continuous flow into your bank account. Doesn't that sound wonderful? Okay, so to give you an idea of where this E comes from, usually this is a common example just to give you the basic idea. If you wanted to see how much money you could make with $1 and kind of max out everything within the time frame of 1 year. So here's the example that's usually done. So let's say we deposit $1 in an account at 100% interest for 1 year. As the interest is added more often, the future amount approaches the value of E. And so I kind of tried to summarize that in this chart here. So if I plug all that into the formula we just looked at, the periodic compound interest formula, 100% as a decimal would be 1. We left n as the compounding because we're going to let that vary. We want to increase it as much as we can. And then the exponent was n times t, and the time here is 1 year. So this n times 1 would just be n. And the one out front would be that $1. So if I use that idea and I take, okay, let me calculate the interest once a year annually, would be $2. I double my money, right, because it's 100% interest. If I do it 2 times a year, I get $2.25. 4 times a year, I get a little bit more. Monthly, so that's 12 times a year. Weekly, daily, every hour. Okay, we could keep going with this. Because we usually round to the penny, I didn't do any more digits out here, but I don't know if you remember the value for E, but basically this is approaching the value for E, which is the 2.71828182845, etc., etc. Okay, so the more we compound the interest, the more often we do it per year, the closer the value of our investment gets to the value of E. This is the idea of a limit, if you've ever talked about limits. Okay, so this piece of the formula allows us to see E in the formula for the continuously compounded interest. And again, that's not a full derivation of where this comes from, but it's a little bit of an idea so you can see where we're going. Okay, so we can plug into this formula just the same. So I took my same example that we did at the beginning, just so that you could see how it compared. So if we have $1,000 invested at 6%, but this time compounded continuously for 3 years, and we want to find the future value. If it's compounded continuously, that's the key word to let us know that we're going to use the PERT formula. Okay, so we have $1,000. We have E raised to the 6% would be 0.06 times 3 years. So that's 1,000 times E to the 0.18 power. I like to do that part first, and then I do the second ln to do my E. And then I multiply by my principal, which is 1,000. Oops, I don't think I did that right. Let's try that again. There you go. So we end up with $1,197.22. And if we compared that with what we did earlier, so here's annually, the interest was added. This was semi-annually, and this was continuously. So we earned $3 more on top of the semi-annually and $6 more annually. This is sort of the maximum we could get, right, from our $1,000 with that interest rate for that 3-year period of time. Okay, and like we said, this $6 may seem like a really small amount, but if we had invested more for a longer period of time, it would grow exponentially, right? It would grow a lot faster than that. Okay, so now that we've given you the formulas and you have the basic idea, now we could do a couple more examples just to try it out. Okay, so this one says, suppose $9,000 is invested into an account that pays 8% interest compounded quarterly. So that's 4 times per year. So N is 4. And part A asks us to find the future value of the investment after 15 years. So we're going to plug into our formula. Since it's quarterly, we're going to use the periodic compound interest formula. Let's see if I can put that up here. Okay, so our principal would be the 9,000 times 1 plus, we have 8% as a decimal. So if I get 8% per year, and I'm going to add the interest 4 times, I'm going to divide my 8% into 4 equal parts. And then when I calculate the interest, I'm going to do it 4 times for each of the 15 years. So 0.08 divided by 4, that's 0.02. So I have 1.02 raised to the 60th power. So if I put that in my calculator, I end up with $29,529.28. Okay, now we're going to add in a question that's really tying together this section with what we've already previously done in Chapter 5. It says, how long will it take for the money in the account to double? Okay, anytime we're asked how long, it means we don't know what the time is we would like to know. And so for this one, the principal was $9,000, and we wanted to double that. So that means that We want the accumulated or the future amount to be $18,000. And we want to know how long does it take to get to that amount. Okay, we're still using that 8% compounded quarterly. So if we put all that into our formula, 18,000 is equal to 9,000 times 1 plus 0.08 over 4 raised to the 4 times t power. Okay, maybe you already made this into 1.02. So now I'm solving for an exponent. And this is something we've done already, but it's, we did it last week. Okay, so let's divide by 9,000. And then I need to use a logarithm at this point. And we've talked about a couple options. You can either convert this into a logarithm, or you can apply a logarithm to both sides. Whatever your choice is, it's fine. For this one, I'm going to convert it to a logarithm. So 1.02 is my base of 2 must be equal to the exponent, which is 4t. So once I get the value for this logarithm, I'm going to take it and divide by 4. And I know we've already talked about this many, many times. Some of you can type that logarithm in directly using the log base. I can't do that. I've already told you that a bunch of times. Okay, you can do that. Go for it. I am going to make the ratio log of 2 divided by log of 1.02. So I get pretty much 35 divided by 4. We'll say 8.75. And that's years. So how long will it take for the money in the account to double? About 8.75 years. All right. Let's try one more kind of the same. Suppose 20,000 is invested in an account earning 8%, this time compounded continuously. That tells us we want to use this formula. Part A, find the future value of the investment after 30 years. So now we have $20,000. And we're earning 8%, so 0.08 times 30. So if I add all that up, looks like I get 22,000. Oh, sorry. That's a lot of growth. Let me rewrite that. That is $220,463.53. That is a good investment right there. Okay, the second part of this question, how long will it take for the 20,000 to double if the 8% interest is compounded continuously? Okay, and same thing is true here. We want to double the this is the principal. So we want the future value or the accumulated value to be double. Okay, and we want to know how long does it take for that to happen. I plug all this into my formula. Principal was the 20,000. I'm compounding continuously at 8%. Okay, but I don't know how much time. Okay, this is separate from part A, so I need a variable for the time because I'm solving for that. Okay, we also just practiced solving these, so we're going to divide by 20,000. Notice we got a 2 here on the left-hand side again. That's always going to happen when we double, no matter what the amount is. If we're doubling, we're going to see that 2. Same thing's true here. You can apply a logarithm to both sides or convert it to a logarithm. The base here is e, so I'm going to have the natural log of 2 must be equal to the exponent. And then I'm going to divide by that 0.08. So I can take the natural log of 2 and divide it by 0.08. That gives me 8.66 years. Alright, well I hope this gave you a really good idea about how compound interest works, what the formulas are, and what's going on in the background with the money that we're doing. Something that I didn't mention, all of these examples were investments. It's nice to talk about our money growing, okay, but the same kind of calculation can be carried out for the interest that you would need to pay for a loan. So it accumulates in the same way, but now we're not earning the interest. We have to pay back the interest. So just so you know that you may see problems that are worded in both ways, where you are earning or where you are paying the interest. Calculations are the same. Good luck with these.